So, hi everyone. In this tutorial, we talk about the analysis that you can do that are built in the HiVis tool. As I said before, HiVis is fully compatible with Scampi and SquidPy and spatial data and so on. So you can do whatever analysis you would like. But also I implemented few analyses that I use regularly to explore my data and also to do differential gene expression and so on. So I will show you now how you can do it. So as before, we load the data. So we have the full data and the subset. This is to demonstrate that you can do analysis also on the objects, not only on the beans, for example, on single cells. So the first analysis is pseudobulk. This is the most obvious. So for example, we want to see which genes are expressed in the intestinal part. So we did a notation in tutorial number 2 of proximal and distal intestine. And now we want to see which genes are expressed in each one. So the easiest thing we can do is we do pseudobulk by intestine part. And then we can do also this I demonstrate on the single cells, but of course you can do it on the beans and so on. Here we can just do without by argument, and this will just give us the expression level of each gene. So now we have this pseudobulk. Now we want to see which genes are the highest and lowest here. So which genes are specific to the intestinal part. And for this, we need differential gene expression. So we do this by our object.analysis.dge, differential gene expression. We specify the what we are testing. So for example, intestine part. We specify group 1 and group 2, so proximal and distal in this case. We can also do, for example, different clusters, cluster 1, cluster 2, and so on. Or we can specify only group 1, and then group 2 will be all the rest. The method is Wilcox. This is to calculate p-value. And in place is if you want to save it inside the var or just work on a data frame. I usually prefer to work on data frame. So now we have this proximal distal data frame. And now we can see which genes have very high log fold 2 change and p-value that is very, very low. So you can, of course, explore it however you like, but this is how I like to look at it. So for example, we see that LCT has a log 2 fold change very high, and the p-value is, or q-value is 0. Similarly, SAA1, it's the opposite. It has a very low log 2 fold change and very low Q value. So now if we look at LCT and SAA and we plot them, we see that indeed SAA1 is far more in the proximal intestine, while LCT is far away in the sorry, I meant this is in the distal and this is in the proximal. So this is very nice. So we did differential gene expression, we found genes, and we validated with plotting that indeed we see these results. So also we can check, as I said, one to all. So this means, for example, we have our single cell and we check our latent cluster 4, what is specific between cluster 4 and all the rest. So if we look at the genes which have the highest and lowest log2 fold change, we have those two here. So we have NPPs, ENPP7 and DEFA26. So if we plot them in the single cell spatial, we see that indeed DEFA21 or 26, sorry, those are in the PANF area. So we can do 26 also. So this is in the PANF area, while ENPP7 is in the epithelial compartment in the villi. So they are indeed very, very different. So now let's say we have a marker. For example, this marker IGLC1, this is in plasma cells marker. So now what we can actually do is we can do our single cell or also beans dot analysis dot core. This is correlation, and we specify the gene. So now if we look at what we get, we have this. So for each gene here, we have the R correlation. So this is the Spearman coefficient. And we also have the expression level and the Q value. So now we also have it in the plot functions. So we can do plot.core and plot the gene. And then we see that those three genes here have the highest correlation with this plasma cell marker, which makes sense because those also are plasma cell markers. Now, if we have multiple genes, we can do correlation metrics by doing analysis.core, but this time specifying a list of genes, not a single gene. And the correlation metrics will look like this. So each gene has a correlation to all the rest of the genes. So we can also plot it using plot.core. And we see that indeed those genes here are clustered together while all the plasma genes are clustered together. So now let's say we have the muscle genes. So those are muscle genes, and we want to find which cells or beans are more muscle-like. So let's now do it on the single cell to find the muscle cells without doing Leiden and annotation and anything. We just know those markers are from muscle. Then we do analysis dot score genes, and we provide this list. We also provide the name, how we call it, and whether we want to normalize or not. This is less critical. So now, if we look at this name that we provided, now we can plot it, and we see that the cells now have a muscle score. For example, the cells here in the muscle indeed have higher muscle score as expected. Now the problem is it's a little noisy because our data is a little noisy and also diffusion and so on. So we want actually to know which gene, which cells are inside the muscle. So how can we do it? We can do smoothing. Smoothing is we use our object dot analysis dot smooth. Again, this could be done on both the aggregation and the bin level object. And we tell it what to smooth. So here we calculated the muscle score. Now we can do this smoothing on the muscle score with a radius of 40 microns. So 40 microns is almost this black line. So in this radius, we will do the mean in this case. We can also do median and log and Gaussian and so on. But and the new column name will be muscle score smoothed. So now when we run it, we will have this smoothed and the normal score. So this is the normal score that we did before, and this is the smoothed one. So we see that it's indeed very smooth. And now we can, for example, say that cells with a threshold above 1, for example, those are the muscle located cells, and work with them and so on. So this is very useful. One more thing I talked about in the plotting tutorial, but this is noise mean curve. And we are doing this by analysis dot noise mean curve. And if we look at the result, we have for each gene the expression level and the CV and the log 10 CV. So we also have the residual from the fitted curve. So we can also do plotting of this, and this is how it looks. So we will have each gene will have an expression level on the x-axis and the log 10 CV on the y-axis. This means how different the gene is in the spatial context, so how patchy it is and how uniform. So uniform genes will be expected to be here on this curve, while genes that are patchy or just very bursty and so on will be higher with higher residuals. The last analysis is how to calculate distances. This can take some time, but what we do is for each bin in this case, we can also do it, for example, on the single cells, but we can do it also on the bins, and we compute the distance to something. For example, in the tutorial number 2, I showed you that we imported annotations, so we have these proximal and distal annotations. And now we want to compute the distance of each bin from those. So when we run this, it takes some time, but when we run this, we have for each bin, 2 by 2 bin, we have the distance to those objects. Now, as you can see, for example, here, this is the largest distance, while here we have a smallest distance because we are near those two. But we can also know which object we are actually closest to. So for example, this bin here, it has a low distance, but a low distance to what? To this one or this one? So we also have this data inside, and this is stored in the nearest column. So here we have we calculated the distance. So we have now this to something, and we also have the nearest something. So if we plot this, we see here that all the bins, now we know which object they are closest to. So I can know each bin, is it a small or large distance based on this, and which object it is. So yeah, so this concludes the tutorials, the HiVis. So I talk about everything. So how to handle the object, how to work with QPath and import annotation, segmentation, how to do single cell, how to aggregate everything into the aggregation object. I showed you how to plot, and here I showed you how to do the analysis. So go explore your data.